Okay, I'm Rick Fleeter, and so, those smartphone people are pretty smart, right? They realized there's no point in doing all this technology just to have a wireless telephone. You can go way beyond that, and it's up to us techies to do it. Customers didn't ask for that. Customers didn't say, gee, guy, could you make a cell phone that I could attach to my car keys so that I could call my car keys if I lose them? My mother didn't think of that app, but she could definitely use it. Very smart people. We are the very smart people in space. We're the ones who are supposed to come up with those ideas and say, hey, look at this that we could do with a little satellite. But we're not doing that. We're trying to replace macro missions with small missions, which is like, okay, replace the line telephone with a cellular telephone. And one of the reasons, okay, we're a failure, and I feel like I'm a little bit of a failure, but one of our failures is that we haven't put the satellite in the hands of other people, of people who are not aerospace engineers. Those are the people who come up with these apps. It's not generally computer engineers, cell phone engineers. It's people who have the smartphone and they write an app, right? I mean, smartphone people did not write Move It. Move It is the GPS for people who want to take the metro, right? So you live in Rome, you use Move It. You say, here's where I am, here's where I want to go. How do I get there? Move It says, walk 100 meters, take the bus number, blah, 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 get off at this exit, get into the metro, take the metro to Rabibia, get off and walk 200 meters, and you're at your destination. It's a GPS that was not written by Apple, that was written by a startup in Israel, and now they have Move It in many, many different cities in Europe and in North America. So that is what we do want to do. We don't want to just replace big satellites with little satellites. It's a dead end. What we want to do is say, what can we uniquely do that's really cool with these little satellites? Since we're not apparently smart enough to think of that ourselves too much, we also need to be more open and get all kinds of crazy people playing with satellites, and that we do know how to do. By scalability, by not requiring everyone to get a license, by Wi-Fi, by using shared spectrum, and making it so that anybody can get into space, somehow solve the launch problem so that you don't have to know somebody, you know somebody, you know somebody, you just buy it, right? You get your launch into space and you have a radio license because you're using shared frequencies the same way that Wi-Fi, you don't have to get a license to get a router. You just buy the router, plug it in. Even if 50 people in your apartment building have routers, it's no problem. They don't say, oh, you can't have a router because your neighbor already got one. I mean, that would be totally lame, right? Then I have a few pages on microspace apps. Of course, my big one, which isn't even really microspace, is space tourism. A friend of mine went to the Paris Air Show, and he said to me, well, it was the same old defense contractors, transport airplane contractors, and the same old people at the booths, all the military guys, all the buyers, people from the big airline companies of the world. He said, totally, I've been to that conference every year of my existence, either Farnborough or Paris, forever, and nothing's changed. The only booth that had excitement was Virgin Galactic. The only booth that had crowds, where people wanted to know. It wasn't just, okay, it's my job to find out what you guys are doing this year. That is a breakthrough app that is going to change space. Okay, the inspection, I think, is kind of an obvious one. We don't even know when we launch a high-powered direct broadcast satellite if the actual antenna pattern on the ground is the one the engineers designed. How do you measure that? Because you can't travel around half of the world and make a grid of but what you could do is fly a small Sentry satellite a few hundred kilometers from that geo and see what the pattern looks like in the relatively far field from the antenna, and then by extrapolation how it will map onto the ground. So there's all kinds of teleoperations that you could do. The idea that I talked about of whole Earth real-time imaging and the rapid updating, those satellites are already being built and launched, but they haven't had their impact yet, right? The idea that we could replicate GPS now that we're so good at it and maybe slave a GPS around the moon to GPS signals that already exist around the Earth so that we could replicate GPS in other places in space, in orbit, because orbital space is not serviced by GPS, and then at least around the moon, and eventually, you drop a probe into Venus, how the heck do you know where that thing is on Venus? The accuracies are just incredibly terrible, right? And then what we used to call in situ remote sensing, which is you drop 1 million sensors onto the ground, and all you're doing is reading out the sensors. It's a perfect application for small satellites. Then I have one slide in here on infrastructure, because infrastructure is part of what will make small satellites much more powerful in the future than they are today. How useful is your smartphone without the internet and the cell network? Two hundreds of billions of dollars pieces of infrastructure, if not trillions of dollars, that make your $600 smartphone really valuable. And yet we don't have that infrastructure in space. Infrastructure is not necessarily going to be done by small satellites, though it could be, but the impact is on small satellites. It's small satellites that don't have the resources to downlink a gigabit per second to the ground 24/7. There's just no way that we know how to do that from LEO. But if we had the infrastructure of a band of satellites that provided a Wi-Fi environment throughout an orbital plane, then we would fly in that orbital plane and have bandwidth capability comparable to any large satellite, which would be incredible. It frees the small satellite to do what it could do. Then this morning I also talked about supply and distribution. It's a small satellite mission to take other small satellites from orbits that are available but undesirable, like geosynchronous transfer orbit, and move them to orbits that are desirable, like 400-kilometer circular low Earth orbit. So how do you do that? You have to have a carrier satellite, and that carrier satellite is basically a P-pod. A P-pod with a little bit of smarts, a P-pod that has a drag device and a small amount of delta V, 20, 30 meters per second of delta V, and that's adequate. So it's not that we can build a cheap small launch vehicle. We can build a cheap small gadget that allows us to leverage space that's already available on large launch vehicles to the advantage of small satellites. You know, cheating is totally legal in life. I'm always saying this to my students. If I give you a design problem, feel free to rip off design ideas wherever you find them. Go out on the internet, go out on Google. I'm like the anti-professor. I want my students to plagiarize like mad, right? I don't care how you put satellites in the hands of 1 million people. Cheat any way you want. And if the way you want to cheat is to say, gee, I can't build a small launch vehicle because I'm not Elon Musk and I don't have $100 million and I don't think it's really possible with today's technology, but I do know how to build a little carrier vehicle that will take satellites from geosynchronous transfer orbit where people go every week of the year with excess capacity, that's totally legal. I don't care how you gave me my kilogram for $10,000, I just want it. And if you cheat by doing it, that's fine with me. Then the idea of enhancing the Virgin Galactic experience with a small satellite that launches from the Virgin Galactic spacecraft and provides a Wi-Fi environment and photographs from a distance, just like a Sentry satellite, for the 10 minutes that it's in the apex, the apogee of the parabolic arc when there's no drag. And then as soon as it re-enters the drag environment, the little hockey puck is blown away by its low ballistic coefficient and disappears. So for a few $1,000s, you build a small satellite whose lifetime, quote unquote, on orbit, on its trajectory, is about 10 minutes. But it provides a tremendous amount of economic value during those 10 minutes, and the good news is it's destroyed every flight. So you get to build a new one every flight and sell it. There have been many examples already of independent constellations and clusters. Most of us don't even realize that NASA flew a constellation of 72 satellites to do geomagnetic mapping of the inner solar system. And how do you do that? I mean, these satellites don't have to be stabilized. They each one have a magnetometer, and all they say is, here's the magnetic field where I am. And you strobe them every minute, every hour, whatever it is, and you get a three-dimensional mapping of the geosphere around the sun. That was what they wanted to do, and there have been several missions already done like that. One of the things that you change when you change the application is you change the users. I really want to do that. And I made a list here of how you change the users. The satellite is not a program of a university. It's a professor who does it in his lab, right? That's a different customer. It's not an organization. It's not an institution. It's a person, right? So you don't sell NASA a satellite to do a NASA science program, and they pick the science, and they pick, no. The scientist is, NASA doesn't give me a voltmeter. Why should they give me a satellite? So if I need a voltmeter, I buy it. So if I need a satellite to take a measurement in space, I'll buy it, right? All of a sudden, we think about satellites differently than we think about every other scientific tool. There's no other scientific tool, except for maybe CERN or a collider or something, where you write a proposal grant to the government to use that tool. You just buy them, right? So you should be able to just buy a satellite. I need to launch this. Where do I buy that? And you go to the internet, and there's like Clyde Space or something like that, and you buy the satellite and you do your mission, and you're not doing it through an organization. Okay, I want to say 3 slides very quickly about how architectures have changed. Because classically, space system architectures were the Battlestar Galactica, as it's called, this huge satellite that did it all, the stabilization, the solar power, the beaming of the signals to Earth, the geo-satellite model of how you do that. The classic space system architecture, a big satellite, highly capable, fantastic pointing accuracy, high power, just a fantastic piece of technology. So, what are the uses of these classical space architectures? Because the architecture really generates what you can do with it. And classical space architectures means you do individual geo-comsats and direct broadcast television and radio. You can do remote sensing, either from GEO or from LEO. And you can do a certain amount of multiple satellite if the number of multiple satellites is not too big. Otherwise, it becomes uneconomical. One of the uses of that was for launch detection. You know, knowing who's launching what around the world requires more than one satellite. TDRS, to provide continuous communications, you need 3 geosynchronous comsats spread at 120 degrees. So we have limited number of what we would call constellations. What I would call contemporary space systems architecture, where we are now, we have a more variety of sizes, and there are numerous constellations up there. Orbcom and Globalstar and Iridium are the ones that everyone points to, but also, of course, GPS, and now that we're on the verge of having 5 different GPS constellations on orbit, it's certainly become a reality. Cosmos SkyMed is really a constellation of radar satellites so that you get more frequent coverage and more geographical coverage than you would have if you only had one satellite. But what we don't have, I mean, that's the kind of current state of affairs. What we really don't have, though, in the emerging space systems architecture, the very first thing that we don't have is a close cooperation among multiple satellites. Despite all the talking about a synthetic aperture, which would be consistent of a number of small satellites that each know exactly where the other one is, and therefore can be optically phase locked one to the other, and you can reconstruct the image from this sparse but rather large baseline array. We don't have that yet. Though it's in the plans of a lot of agencies and a lot of people to do it, that is an emerging space system. Emerging in the sense that we kind of have the idea of how we're going to do it, but we haven't yet done it. And we don't have infrastructure. We don't have orbits with infrastructure. We know how to do that. I don't think we realize the power of doing that. And then, of course, the Federation. So we've kind of talked about these are the architectures of future satellites. I mean, in a way, the infrastructure that I was talking about is an infrastructure that is built specifically to do that job. Whereas the federated system may be for that job, or it may just be opportunistic and use whoever's up there. But in some ways, cooperation among the satellites, active cooperation to provide a capability that is not possible with any one alone. Whereas TDRS satellite number 1 doesn't know or care what TDRS satellite number 2 or TDRS number 3 is doing. So if we have a network of VSAT, very small aperture ground terminals, talking to satellites, VSAT satellites they call them, there's a lot of them up there, but each one operates independently, serving its geographical area. In a federation, you have cooperation among satellites. That is absolutely the future of particularly small satellites. It's something that small satellites are uniquely qualified to do because you need lots of them. And it's not that big satellites couldn't do it. They certainly could, but nobody's going to be able to pay for it. So the only way to do those missions is if they're small. The only way to do inspection is if it's small. Because otherwise, why build an inspection satellite that costs as much as the other satellite, particularly to launch it? So there are certain missions that only make sense if you can do them on a small. And then on the technology side, what are the emerging technologies that are going to change things? One is large deployables. Despite the lack of attention that the world pays to deployables, they are absolutely critical to particularly miniaturizing satellites. Reduced entry barriers, meaning we have to get rid of licensing. Licensing for radios is something out of 50 years ago, and we still do it. And we still force people to pretend as if they're ham radio operators so they can use J-band, transponders and transmit up on the ham radio 432 megahertz and down and transmit up at 144 megahertz. This is something AMSAT was doing in 1961. It's crazy. You don't buy a Wi-Fi hub, you don't buy a smartphone, you don't buy anything now. Of all our wireless devices, nobody asks you to get a license. But then you want to build a CubeSat with a bunch of high school students, and they treat you exactly as if you were a geosynchronous satellite comms operator looking, to download 300 channels of HD TV. I mean, it's absurd. It's totally absurd. So we don't like to think about that because we're techies, right? We don't think about reliability. We don't think about management. We don't think about politics. But politics is going to be a part of the key to changing how we use small space. I think having high bandwidth crosslinks is a part, when you talk about technologies, if the federation is going to work, you're going to have that kind of a thing. And not just for that, but also if your attitude is going to be sensed remotely, which we can do the sensing, but how do you do the link? I have to have a way of reading your sensors on my other satellite and sending back to you the controls to change the velocities, the rotational speeds of your wheels to control your attitude. Really, the problem is only in the cross-linking between the satellites. That's a hard part. The rest of it is already solved. So to have autonomous control of numerous satellites without burdening each one with a control system only requires, at this point, the cross-linking. So we need that. And of course, new applications that we don't know what they are, which are only going to be invented as we push the satellites down to less and less entrenched aerospace-type users. I have a couple slides on NASA Constellation metrics. They have a whole stair-step pattern of where constellations are going, starting with the magnetomapping mission that I mentioned and going all the way up to nanometer-controlled constellations of satellites to do planetary imaging and stuff like that, which they claim is going to happen, in 2009 when they made this forecast 5 years ago, they claimed it was going to be 2025. So maybe now it's going to be 2030. So if you extrapolate that, it's never going to happen. But I think it is eventually going to happen. And then the second one is basically metrics on how many satellites we can cause to cooperate together. And as of 2009, we at least knew how to measure our relative positions within 10 meters or something like that. And there were autonomous operation, and I participated in one of those missions of like 5 satellites. But the idea for 2020 is to know your relative position relative to another satellite within 0.5 of a nanometer. So you're talking about being able to share an optical signal among satellites, have a small collecting mirror on 100 different satellites that each know their position so well that you can reconstruct the actual optical image from that satellite. And that's the NASA prediction will be here in 10 years type number. Another application I call the synthetic ionosphere. How come I can't just turn on an S-band radio and pretend as if it was reflected off the Earth's ionosphere? You could do that. You could have a whole bunch of satellites in orbit reflecting those signals back and basically extend the ionosphere to higher frequencies where the ionosphere is actually not reflective. And why would you do that? Because it's a very simple way to have communications. I don't want to know about satellites and linking to satellites and pointing at satellites. All I want to do is what ham radio operators did 60 years ago, key the transmitter, and somehow or other my signal bounces around the globe and somebody over the horizon picks up my satellite. And we have had those missions demonstrated in a single arc, in a single necklace, they would call it, where while that necklace was overhead, you just turn on your VHF radio and you can reach people all around the world who are under that same necklace. So that would be a nice application of a few hundred small satellites that were each one of them just a dumb wideband repeater. Whatever I hear, I reflect it back down. That's what the ionosphere does. The ionosphere is just a mirror, and it takes whatever signal you send to it and it reflects it back down. So we just want to build a couple hundred satellites that do the exact same thing, and therefore you can turn on your S-band or L-band radio, transmit, and reach every place around the world. We talked about the Student Space Telescope. We've talked a lot about CubeSats. I just wanted to mention that there used to be in Europe a big project, the AMSAT Italy was involved in it, called Astrosat, which was the Student Space Telescope built by amateur astronomers. And boy, I'd still love to see that. So, my own bias, predicting the future of small satellites, we've got to do that. It's just something that we really want to do. And entertaining missions that are just done for the entertainment of it because they help to bring new people. I used to be a bicycle racer, and when you're a fairly high-level bicycle racer, I was kind of not the greatest bicycle racer, but I was racing, in a couple of different countries and, not very good. I never won anything, but I was there. And as a bicycle racer, you tend to look at other people on bicycles as being it's kind of elitist. It's kind of being unnecessary. what is this person, this older guy on a bicycle, these kids, these people riding around town commuting to work on 3-speed bicycles, they have nothing to do with me. That's totally wrong. Because every person riding a bicycle contributes to bicycling as a sport, because there's more factories, there's more competition for business, prices go down, cars see more bicycles on the road, kids see bicycles, wow, that's cool, I want to do that someday. So every addition to the population is as valid as any other addition to the population. And sometimes those normal people, what we called normal people, using bicycles to get to work. I was talking to a couple of other, racer types one day, and I said, yeah, riding around Rome now, you go to work, and you don't just see us bike nuts riding to work. You actually see normal people riding to work. You want those normal people using satellites, because that creates the industry that then has the muscle to do really sophisticated things. And out of every 1,000 little kids who are involved in bicycling, one of them may be a great athlete, and that's the guy. And you think, well, I could have just had that guy, and what do I need the other 999 for? Sure, hindsight is 20/20, but that guy wouldn't have gotten involved in bicycling if 1,000 of his friends and contemporaries also weren't doing it. So it's a critical thing that we incorporate new people. I think that that ability to reach out to more people is the difference. Not every mission needs to be big in order to be done. When big is not necessary is when you're measuring fields and fluxes and space weather. You want to do a mission that's intrinsically small, like radio astronomy or something like that, where all you really need is a receiver, and maybe you want many point receivers. Robotics, servicing missions, and missions that are specifically built to be for students are automatically small. Here's a bunch of things that we don't even think about right now that ought to be on our agenda. And one of them is on-orbit servicing, right? We have no on-orbit servicing. We have no way of getting to a satellite and figuring out what's going on with it. On-orbit services in the terms of analyzing the satellite, and then on-orbit services in terms of providing comms and remote sensing and those sorts of things of the attitude. We don't have anything like the interstate highway system, and nobody is even talking about it. So that's a bad starting point, right? But that's how the future gets started. We know those things are out there, not even talking about it, so a little bit of activism to get people talking about it. We don't have federations. We don't have particles of satellites that participate with other particles of satellites to create holes on orbit that'll do things, and we don't have modern components. We don't have space-qualified modern components, and we're still compromising what we can do in space because we don't have those things. And just to wrap up on my last slide, something I've been saying all through this talk, my own killer application for microspace, I totally dodged that question. As far as I'm concerned, my job as a satellite geek is not to come up with the apps. It's to build the platform. Like I always say, to me, my role in life and my company's role in life, we're violin makers. Doesn't mean we know how to play the violin particularly well. I can play the violin, like if I were a violin maker, I could play the violin well enough to see if it's like in tune, right? But I want to give that violin to a great violinist and let him go wherever he wants with it. And so I don't try to be a composer, and I don't try to be a musician. I try to put that violin in the hands of people who can make beautiful music with it. And that's my microspace killer app. We should be putting satellites in the hands of people, which is in a way crowdsourcing. We want to crowdsource our ideas, get enough satellites out there that all kinds of crazy people are using them and tell us what they want to use satellites for, instead of us trying to top down say, what the world needs now is this other thing. And that's my future of 100 years in microspace, 57 in the past and 43 to go. Thank you.